Let's recap the concepts of locus and also constructions. Now, locus is a Latin word which means locality or location, but in maths, locus is the path traced by a moving point which moves so as to satisfy certain given conditions. Now, what does it mean? We can look at some locus theorems. In your syllabus, in ICC syllabus, there are exactly 3 theorems. So, the theorem will have a given condition and they will tell what is that path traced by a moving point which will satisfy those given conditions. So, here the given condition is that I need a moving point which is always at a fixed distance from a fixed point. So this is my given condition, and according to the theorem, the path of that moving point will be a circle where the fixed distance that they were talking about in the condition is the radius of the circle, and the fixed point in the condition is the center of the circle. So let's look at this figure. Imagine that O is the fixed point given, and we have a length of 5 centimeter, and that is my fixed distance. So if I try to move 5 centimeter away from point O, I will be able to move exactly in the shape of a circle. So if I move 5 centimeter from point O, I will again reach wherever I started, and that entire path, if I draw it, it will be a circle where O is the center of the circle and the fixed distance, in this situation 5 centimeter, is the radius of the circle. So if I select any point, let's say point A on that locus, A is always going to be 5 centimeter away from the fixed point O. Then the next theorem has the given condition that I need a moving point which is always going to be equidistant from two intersecting lines. And according to the theorem, the path traced by this moving point will be the bisector of the angles between the two intersecting lines. So in this figure, L1 and L2 are two intersecting lines, and they are forming some angles between them. They are exactly forming two vertically opposite angles, two pairs of vertically opposite angles. So one pair is the blue angles. If I draw the bisector of the blue angles, I will get this straight line like this. So this line is the path of the moving point, which is always going to be equidistant from the lines L1 and L2. So if I had selected any point, let's say point A on this angle bisector, and then if I look at the distance between point A and line L1 and line L2, I always look at the perpendicular distance whenever I am talking about the distance of a point from a line. So if I draw perpendiculars, so if I label it B and label it C, AB will be equal to AC. Now I also have another pair of vertically opposite angles, the yellow colored angles. If I draw the bisector of those angles, I will get another straight line like this. And if I select any point on this line now, let's say this point D, again D is going to be equidistant from L1 and L2. If I draw perpendiculars on L1 and L2 and label it E and F, I will see that D will be equal to DF. So in case of two intersecting lines, the locus of a point which is equidistant from the lines is going to be the bisector of the angles between them. Now, instead of two lines, suppose if I consider line segments, let's say AB and BC are two line segments, or I can also consider them as two rays, BA and BC. So then if I look at what is going to be the locus of points which are equidistant from AB and CB, it is going to be the bisector of angle ABC. So if I draw the bisector of angle ABC, I'll get this line. So this line is the locus of all the points equidistant from AB and CB. Then the last locus theorem is talking about the given condition where I need a moving point always equidistant from two fixed points. And according to the theorem, the path traced by this moving point will be the perpendicular bisector of the line segment joining the two fixed points. So let's say that I have point A and point B as the two fixed points. Then the path traced by a moving point which is always equidistant from points A and point B is going to be this line, something like this. And this is the perpendicular bisector of the line segment joining A and B. So if I join AB, I have this line segment AB now, and this line which I have drawn as the locus is the perpendicular bisector of AB. So if I choose any point on this line, let's say I choose point C, then C will, if I join AC and BC, AC will always be equal to BC. So these are the three locus theorems that you need to know. Now there are some couple of more concepts which are somewhat related. So the concept which is quite important for you to know is about four centers of triangles. So if I take any triangle, I can talk about four different types of centers. So the first center is the centroid of a triangle. Now centroid is the intersection of three medians. Median, if you remember, is the line segment in a triangle starting from one vertex to the midpoint of the other side. So for example, if I choose point A as one of the vertex of triangle ABC and the other side's midpoint, the other side is BC, the midpoint is point D, then ED is one median. Similarly, if I say BE is another median, CF is another median, then the intersection, or another word for it is also the point of concurrence. That means the point of intersection of two or more lines. So that point of intersection is known as the centroid. So here I have labeled G as the centroid of this triangle. And always you should remember that the centroid of a triangle is located on the median such that it divides the median in the ratio 2:1. So here AG is to GD is 2:1. BG is to G is also 2:1. CG is to GF is 2:1. Then another center is orthocenter, and it is the intersection of three altitudes of a triangle. Altitude means the line segment which is from one vertex of the triangle perpendicular to the opposite side of the triangle. So if I draw all the three altitudes of the triangle, then the point of intersection is known as the orthocenter. Here I have labeled O as the orthocenter. Then another center of the triangle is circumcenter. Now circumcenter is actually the center of the circle which passes through all the three vertices of the triangle. So if I have triangle ABC, the circle which I have drawn is the circumcircle, and the center of that circle is known as circumcenter. Here I have labeled O as the circumcenter. Now, since this circle is passing through all the three vertices A, B and C, and O is the center, OA, OB and OC are the radius of the same circle, which you know is always equal, and that radius is known as circumradius. So that's why OA, OB and OC are all equal, which is the circumradius. Now O is also equidistant from all the three vertices of triangle ABC, and because of that reason, if you remember the Locus theorems, any point which is equidistant from any two fixed points is going to be on the perpendicular bisector of the line segment joining the fixed points. For example, let's look at the circumcenter O being equidistant from fixed points A and B. Then that point, the circumcenter, must be on the perpendicular bisector of AB. So if I look at the line segment AB and draw the perpendicular bisector, then this circumcenter will be a point on that perpendicular bisector. Now, since the circumcenter is equidistant from A, B and C, I can also look at the side AC and BC. So the circumcenter must be lying on the perpendicular bisector of AC as well as BC. So actually the circumcenter is located on the intersection of the perpendicular bisectors of all the three sides. So it is at the intersection of the perpendicular bisectors of the three sides of the triangle. Then the last kind of center of a triangle is incenter. So if you have a triangle ABC, and if you imagine that we can draw a circle inside the triangle in such a way that the three sides of the triangle are tangents to the circle, then that circle is the incircle and the center of that circle is incenter. So let's say that ABC is my triangle and I have drawn this circle inside it where O is the incenter. Now since AB, BC and AC, these three sides of the triangle are acting as tangents to the circle, I can label P, Q and R as the point of contact between the tangent and the circle. Then if I join OP, OP is the radius and it should be the same as OQ and it should be the same as OR. So OP, OQ and OR are my in radius. Now point O is the center of that circle, center of my incircle, and you know that from your circle and tangent theorem, if OP is a radius and BC is a tangent, OP is perpendicular to BC. Similarly, OQ is perpendicular to AC, OR is perpendicular to AB. And since OP, OQ and OR are the radius of the same circle, they are all equal. So I can also look at point O as being equidistant from AB, BC and AC, because OP represents the distance of point O from the side BC. OQ represents the distance of point O from the side AC, and OR represents the distance of point O from side AB. So you can see that point O, which is the incenter, it is equidistant from AB, BC and AC. So I can say that the incenter is always equidistant from all the three sides of the triangle AB, BC and AC. And also according to the Locus theorem, I know that if I have a point, let's say point O, equidistant from two intersecting lines AB and BC, then it should lie on the bisector of the angle between AB and BC. So if I draw bisector of angle B, point O will lie on that angle bisector. Now O is equidistant from all the three sides, so O should be lying on the bisector of all the three angles, angle A, angle B and angle C of this triangle. So if I draw bisector of angle A, if I draw bisector of angle C, so point O, the incenter, actually lies on the intersection of all three angle bisectors, the bisectors of all three angles of the triangle. Now suppose these things we were discussing for any triangle in general, but in the specific case of an equilateral triangle, because it is very symmetrical, all the four centers for equilateral triangle will be the same point. It will be a coincidental point where all the four centers are actually on the same point. Now we apply whatever we discussed till now to construct circles and tangents in different situations. So here as part of your chapter of constructions, you will have to construct circumcircle of a triangle or a regular hexagon. So like we discussed that suppose whenever the question is about constructing circumcircle or a circumscribed circle to your triangle or regular hexagon, first thing anyway you will construct the triangle or regular hexagon with your scale and compass. Then to draw any circle, you need to locate two things. You need to know two things. One is where is the center and what is the radius. With a center and a radius, you can always draw a circle. So if you want to draw a circumcircle, which is the circle around the triangle or regular hexagon, you need to locate the circumcenter. And as we discussed, the circumcenter is located on the intersection of perpendicular bisector of the sides. Now, if you are able to construct the perpendicular bisector of any two sides and wherever they intersect, that point is going to be your circumcenter. That point of intersection is your circumcenter. Now, once you have located your circumcenter, you need to know your circumradius. So for example, I have a triangle and a regular hexagon. Let's say I have triangle ABC. And the first step, construct perpendicular bisectors of any two sides. So let's say AB and BC. We will look at another video where we will do the construction of perpendicular bisectors. Let's say that they intersect at this point. This is point O, and that is going to be the circumcenter. Then the radius is equal to the length OA, OB and OC. So let's say you take the length OB as the radius of your circle, take your compass, put the center at point O, take radius equal to OB and then construct the circle. So you will get a circle which passes through all the three vertices of triangle ABC. And in case of a regular hexagon, again you can draw the perpendicular bisectors of any two sides. For example, you choose bisector of this side and this side. So this intersection point is going to be the circumcenter of that regular hexagon. And then a regular hexagon has 6 vertices, A, B, C, D, E, F. You can choose, let's say, the length OA as the radius. And then with the center O and radius OA, you will be able to draw a circle which passes through all the 6 vertices of your regular hexagon. So that is construction of circumcircle. Then to construct incircle, again it's the same concept. First draw your triangle or regular hexagon. Then to locate the incenter, you know that it's the intersection of the angle bisectors. So take any two angle bisectors and the point of intersection is incenter. So suppose you have triangle ABC, bisect any two angles, let's say angle A and angle B, and you get your point of intersection, let's call it I. Now you need the in radius. So you know that from point I, you have to draw a circle and the sides AB, BC and AC are tangents to the circle. So from point I, you have to draw a perpendicular to any one side. So let's say I am drawing a perpendicular to the side AB. Again, that construction using a compass, we can have a look when we are solving a question. Now, let's say this is point P. So IP is the perpendicular from point I to the side AB. So IP will be the radius, the in radius. So looking at that in radius, if you draw the circle, it will be something like this. You will get the incircle. Same way for a regular hexagon, you draw the bisector of any two angles, let's say angle A and angle B, and they intersect at this point, so label it as point I. Then again draw a perpendicular to any one side of the regular hexagon. Again, if you call it P, IP is the the in radius. Then with IP as the in radius and I as the center, you draw your incircle. So all the 6 sides of the regular hexagon will be tangent to the incircle. And then the last thing is to draw tangents to a circle. There can be two situations. Let's say that you have a circle and there is a point on the circle, let's say point A, and you have to draw a tangent to the circle at point A. So then first thing is, you will already draw the circle with whatever center, let's say point O is the center of the circle and A is where you have to draw the tangent. Then join OA, and OA is going to be your radius. Now you know that the radius and tangent are perpendicular. So then draw a 90 degree at point A. So draw a perpendicular line to OA at point A, again using compass, and if you are able to do that, and then let's say this is P, then AP is your tangent, which is perpendicular to the radius OA. Now suppose if you have to draw a tangent to a circle from an external point, you know that you will be able to draw two tangents from that external point which are going to be of equal length. So let's look at this figure. Let's say that this circle is known to you with some center and some radius. So first you draw this circle with center O. Radius will be given, and it will also be given that there is an external point P. Usually they will mention how far is this point P from the center of the given circle. So then you locate where is point P and join OP. Then try to find the midpoint of OP, not by using a scale but use perpendicular bisector construction. So if you do that construction, let's say this is the midpoint of OP. Let's call it O dash. Now with OP as the diameter, you have to draw a circle, or you can also consider O dash as the center and O dash P as the radius. Draw a circle. So your circle will look something like this. Then you have two circles now, and there are 2 points of intersections. Let's call it A and B. Then join PA and join PB. PA and PB will be tangents to the circle with center O. And the reason is that because you have drawn the second circle, which is on the right side with red color, and you have taken OP as the diameter. If you join OA, then angle OAP will be 90 degree, because you know that angle in a semicircle is right angle. And if you consider the first circle, the left circle with black color with center O, OA is the radius, and I have a line PA which is 90 degree with my radius OA. So therefore AP has to be a tangent, and similarly BP is also a tangent of equal length.